Welcome to the 42nd lecture on computational mathematics with SageMath. In this lecture, we will look at an application to singular value decomposition to image processing. But before that, let us look at how to find singular value decomposition step by step using SageMath. So let us start with an example. So suppose we have a matrix A which is 2 cross 4 matrix. We want to find its singular value decomposition. Okay. So first let us define this matrix A. Now instead of finding singular value decomposition of A, we will find singular value decomposition of A transpose. A transpose is going to be 4 cross 2 matrix, and in that case the matrix V in the singular value decomposition will be 2 cross 2. So it will be easier for us to find eigen values and eigen vectors of 2 cross 2 matrix. Okay. So let us define B to be A transpose and then define B transpose B as BTB. So we need to find eigen values and eigen vectors of B transpose B. So B transpose B is 6 3 3 6 matrix. So let us find eigen values of B transpose B, and the eigen values are 9 and 3. So sigma 1 will be square root of 9, sigma 2 will be square root of 3. So let us store this sigma 1 and sigma 2 in S1 and S2. So S1 is 3, S2 is square root 3. Next let us define this matrix S or the matrix sigma. So this sigma matrix is going to be the first row will be S1 0 0 and second row will be 0 S2 0 0, and we need to take transpose of this because this matrix B is 4 cross 2, therefore the S in SVD will be of order 4 cross 2. So this is the matrix sigma. Okay. Next we need to find eigen values and eigen values we have already found of B transpose B. Next we need to find eigen vectors. So let us find eigen matrix underscore right of B transpose B, and it gives you the diagonal matrix and the diagonalizing matrix P. So here P is 1 1 minus and 1 minus 1, that means 1 1 is eigen vector corresponding to eigen value 9, and 1 minus 1 is an eigen vector corresponding to eigen value 3. Okay. So let us store this in V1 and V2. The first column of P we will store in V1, and second column of P we will store in V2, and since we know we need V to be orthogonal matrix, we will divide V by its norm and V1 by its norm and V2 by its norm. So this is what we get, and let us ask it to show what are V1 and V2. So V1 is square root 1 by 2 into square root 2, that is 1 by square root 2, 1 by square root 2, and V2 is 1 by square root 2 minus 1 by square root 2. So we have got this matrix V matrix. The first column will be square root 1 by square root 2, 1 by square root 2, second column will be 1 by square root 2 minus 1 by square root 2. Right. Now we can define, once we have got V1 and V2, we can define U1 U2 of the matrix U. Right. U here is going to be 4 cross 4 matrix. So U1 will be 1 upon sigma 1, which is S1 here. So 1 upon S1 times B times V1. Similarly U2 will be 1 upon S2 into B times V2. It is easy to check why we are defining U1 and U2 like this. It is not difficult. So if you just look at the way A is decomposed, this is how you will get. Okay. So let us define U1 and U2. So we get U1 and U2 using V1 and V2. So we can find U, the first R columns of U by this method, because we cannot take reciprocal of 0. So here first R columns of U you will obtain using this, where R is the rank of this matrix. So these are U1 and U2. So let us ask it to show what are U1 and U2. This is U1 and U2, and you can so next we need to find what should be the other two columns of U, namely U3 and U4. So remember, U3 and U4 has to be perpendicular to U1 and U2, right. So in particular U3 and U4 has to lie in the orthogonal complement of the subspace spanned by U1 and U2, which is nothing but column space of B. Therefore U3 and U4 will be in the orthogonal complement of the column space of B, but that is nothing but null space of B transpose, which is nothing but left kernel of B. So let us find this left kernel of the matrix B. We know that this is the left kernel, right. Next let us store this vector, first vector in U3 and the second vector, that is second row of this basis matrix, in U4. So let us how do we do that? First let us find the basis matrix of this subspace of the left kernel, take the columns, take the transpose of this, take the first column, that will be give you the first row. Similarly if I take the second column, that will give you the second row of this, right. So let us store these two columns in U3 and U4. So that is what we have done, and once you have obtained U3 and U4, this may not be orthogonal orthonormal vectors, so you need to divide by its norm. So let us divide by its norm, and this is what you get. So these are your U3 and U4. You can check that this U3 and U4 are also orthogonal to each other, and not only that, this is perpendicular to U1 and U2. If you notice here, the way we defined U1 and U2 by this formula 1 upon sigma 1 b times V1 and 1 upon sigma 2 b times V2, you can directly check that U1 and U2 are orthogonal. In fact, they are orthonormal vectors. So that is easy exercise. Now let us define the matrix U, which is column matrix of U1, U2, U3, U4, and matrix V as column matrix of V1, V2, V3, sorry, V1 and V2. There are two vectors only, right. Now you can ask it to show what are U. So this is U, and this is the sigma, and this is the V. Therefore we have obtained singular value decomposition of B, right. So you can check that U into S into V should be equal to B. Next, actually this should have been V transpose, but V in this case is symmetric, so V transpose will be itself. Now you can also check that if I take the transpose of this U into S into V transpose, that you should get as A. So therefore singular value we have obtained singular value decomposition of A. So this is going to be V into S transpose into U transpose. So if you want, you can call this as U1 as V transpose, U1 will be V in this case, and S1 will be S transpose, and V1 will be U transpose, and then when you multiply U1 S1 V1, this will be transpose, you should get this as I think it is be A, right. So this is what you get, right. So this is how you can find step by step this SVD decomposition, but you can also verify this using inbuilt function. So let us change ring of A to RDF, so that this decomposition will work, and find the SVD decomposition and store this in U1 S1 V2, and then let us look at what are these matrices. Of course these will be in decimal numbers, what we have found obtained in square root, but you can check that this is approximation of what we have got, right. So this is how you can find singular value decomposition of a matrix step by step, but of course this you will be able to do mostly when you have a very small matrices. If it is a very big matrix, doing this computation will be quite challenging manually, right. So of course using Sage you can always execute this, right. Now let us look at an application to singular value decomposition to image processing, basically image compression, right. So let us recall that if A has singular value decomposition as U into sigma into V transpose, where U we will write as U1 U2 UM and V will write as column vectors V1 V2 Vn, and here sigma is this matrix which is suppose A is M by N matrix, then this sigma will be M cross N matrix of this form, where sigma 1 sigma 2 sigma r are singular values of A, and with the condition that sigma 1 is bigger than equal to sigma 2 is bigger than equal to sigma 3 and so on, right. So we are assuming rank of A to be R. Now if you just multiply this U S in U sigma into V, this is how you will be able to get this. So A is equal to sigma 1 times U1 into V1 transpose, sigma 2 times U2 into V2 transpose, plus dot 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 sigma R into UR into VR transpose. If you notice, U1 and U2 both are column vectors, therefore both will have and they are orthogonal matrices, therefore it cannot be non-zero. Therefore each U1 and V1 is numerically Ui and Vi will have rank 1, and therefore this multiplication will also have rank 1. So A has become sum of rank 1 matrices, namely R of them, and that is why the rank of A is R, right. Therefore suppose we take only first k component of this sum on the right hand side, this is sigma I Ui into Vi transpose, I going from 1 to k, and as k goes to R, this left hand side will be equal to A, right. So this is so this we can think of as a approximation of this matrix A, right, as a rank 1 approximation, sum of rank 1 matrices. Now what happens is that when we know that sigma 1 is the largest, followed by sigma 2 and sigma 1. So in case you have very large matrix, it is possible that last few sigma i's will be very close to 0, and so therefore most of the information about A are contained inside first few elements of this sum, okay. So that simply means that you can ignore last few components in this. So first few components itself will be very good approximation of A. So this is what is used in image compression. So let us see how we can use this in order to approximate or compress an image. So before that, let us just take an example. We have generated a random matrix which is 300 by 300, and in such a way that first R eigen in such a way that first R eigen values will be random number between 0 and 100, and remaining R could be 0 and 1. The remaining n minus R could be 0 and 1. Okay. So there is an inbuilt function called random underscore matrix, which you can generate a random matrix over ZZ or QQ, and this could be diagonalizable matrix. So here this is a diagonalizable matrix, and whose eigen values are this some n random numbers, and what we have done is we have said that the last, let us say first 50 are random, first 50 eigenvalues are some random numbers, random integers between 0 and 100, remaining R could be 0 or 1. So lots of eigenvalues will be 0 in this case. So let us run this. So this has an inbuilt method to generate a diagonalizable matrix with eigenvalues mentioned in that. Of course, you should also need to mention what should be the multiplicity, algebraic multiplicity of each of these eigenvalues. So, this in this case it says that algebraic multiplicity of each of these eigenvalue is 1, right. So, therefore, it is diagonalizable, right. Now, let us change the ring of A to RDF so that we can find its eigen singular value decomposition. Now, let us find singular value decomposition of this M, which is the A changed over RDF. Next, let us find out what is the difference between the matrix A and the matrix S into U into S into V transpose, singular value decomposition of M. So, the length of this should be very close to 0. Since it is a numerical approximation, numerical way of computing this singular value decomposition, you may not get this difference to be norm of this difference to be 0 exactly, but it will be very close to 0. So, it says that it is of the order 10 to the power minus 10. Now, suppose instead of taking all the terms, all the R terms here, we take for example only first let us say few terms. So, let us take only first 10 terms. So, first 10 terms, how will you obtain first 10 terms? You take first all the rows and first k columns of U, then take first k rows and k columns of S, and then take only first k rows of V transpose. Okay. So, that is, and here k is 10. So, we are taking first 10 elements in this sum, right. So, let us see in this case what is the difference between the norm of the original matrix M and this matrix. So, this in this case it is 73.77, which is quite large as an error, but instead of 10, if I make it 50, then it has reduced considerably, right. If I take instead of 50, if I take 100, it will be again very close to 1, right. So, in this case, because lot of entries in this matrix is going to be almost close to 0. So, that is why you are able to, so what it means is that first 100 terms in this matrix, which what is the order of this matrix? 300 cross 300. So, if you just take first 300 terms of this matrix, you are getting very good approximation. If I have taken all of them, let us say 300, you will get again close to 0, right. So, this is what we will use in case of compressing an image. So, let us take an example. So, let us import an image, let me plot. So, the Sage Math has a function called matrix underscore plot. So, using which you can plot any matrix. So, what we have done here is, actually this is just a Python command. So, from matplotlib by plot, we have imported a function called image read, and then import pylab, and then inside pylab there is a function called image read. Actually this is not required, this is not required, and then we are reading an image. The name I have given is sardar2.png. This is image of Statue of Unity, right. So, when we plot this, so what it has done, it has converted this into okay. So, this is the image we have, right. Now, what we are going to do is we will convert this image into a matrix. So, how do we do that? So, in order to, first before that, let us look at what is the order of this matrix. The order of this matrix is 995 by 1770. That is quite large matrix, that is very big matrix, because this image has very good resolution, and this third component that gives you the color. So, this is a color image, but we have done singular value decomposition of the M by N matrix. So, we need to convert this into gray image, so that this color component we do not have. So, now what do? We convert, there are several ways in which one can convert this color image into gray image. there are several inbuilt methods, but this is the transformation generally one uses. So, red component take 29%, 9%, green component take this, and this is the blue component. So, this is what we will use to convert this image into gray image, and this is what you have. Now, this image is converted into gray image. It does not look all that great, but however it will retain the dimension. So, now let us look at what is the shape of this image. So, it is 995 by 1770. Now, what we will do, we will find singular value decomposition of this matrix. This is a very large matrix, and if you find singular value decomposition, it may take some time, maybe few seconds, depending upon the speed of your computer, right. So, it has done, it did not take too much of time. So, it has found out singular value decomposition of this matrix, which is the matrix associated with this image. Image consists of pixels, each pixels can be thought of as a matrix entry, right. So, now you can find out what should be the dimension of each of these U, S and V. U has 995 cross 995, S is 995 cross 1770, and V is 1770 cross 1770, right. Now, let us approximate, let us take only first 5 terms of this sum, of this sum, only first 5 terms of this. So, that will be an approximation of A using first 5 terms, and then let us try to plot graph of that approximation. Okay. So, let me get rid of this. So, if I take only first 5 terms of this approximation, so you are taking first 5 columns of U, 5 rows and 5 columns of S, and first 5 rows of V transpose, and then if you plot this using matrix plot, this is what you get. So, you can hardly make out about this image, because this is, so this is not a very good approximation. Let me reduce the image size. So, I will say show this and image figure size equal to, let us say 4, or let me make it 5. Yeah, so this is slightly better. So, this is what you get. Now, let us increase the number of terms. So, instead of 5, let us make it 10. So, when you make it 10 approximation, now you can see here this several things. I mean, this is much better than the previous one. It also looks like that you have several of these iron poles, and this is a kind of a statue, right. So, instead of 10, if I make it let us say 30, then it will be much better. You will be able to see this is almost quite clear, and if you take about let us say 100 terms, or let us just take 50 terms, then the approximation is again very much clear, right. So, you see that the first 50 terms itself gives you very nice approximation of the original image, whereas, so first 50 terms in this case will if you compare the number of entries in first 50 terms of this approximation compared to the original matrix, that is a substantial difference in this. So, lot of space is saved, right. So, this is what is called matrix image compression. So, right. Next, let me just run this a loop, so that here it is showing you approximation of starting with first one term, then 11 term, then 21 terms, and so on. So, let us run this loop. So, first approximation is, you cannot make out anything. This is the first 11 term, then 21 term, then 31 terms, 41 terms, and you can see here when you reach about 100, the approximation is very good, right. It is almost like a original, right. So, that is what is called image compression, and that is an application to SVD. This you can also just ignore all the diagonal entries which is less than 250 in sigma, and then that is what we call this as denoising this matrix. So you take them some threshold value and get rid of those diagonal entries, and then in this case if you try to plot this graph, so this is again quite good compared to the original one. So this is another way of denoising matrix. So this singular value decomposition has several applications. One of them is in image processing, and it has many more applications. For example, in data science they use singular value decomposition as dimensionality reduction algorithm, and in this case you can see here instead of taking all the R terms which is rank of this matrix, we have taken only first few terms. So you have reduced these several components of this, and still you are getting very good approximation, right. So let me stop here. We shall look at more applications in next class. We will look at application of linear algebra to solving system of linear equations. That will be again an application of eigenvalues, eigenvectors. Thank you very much.